Welcome to Concept 47, Introduction to Trigonometry. A few of you have a little bit of background in this area, but for most of you, this is going to be something that is brand new. You might have seen buttons on graphing calculators before that look like this. They say these letters, and you might have thought it said sin, cos, tan, but it actually stands for sine, cosine, and tangent. These are actually ratios, and we're going to learn what they mean today. So we're going to start with this first sentence that just says a right triangle with a 35-degree angle is similar, that's why we're learning this in this unit, similar to every other right triangle with a 35-degree angle. Okay, let's sort of unpack this statement. Basically, it could be made for a right triangle with any angle. That 35-degree angle is not anything magical here. I just picked a number. And then we're going to look at a triangle that happens to have that degree angles later today. So if you have a right triangle, if you know it's a right triangle, which means you already know it has a 90-degree angle, and then that triangle also has a 35-degree angle. So I'm just going to make a sketch here. This is not going to be accurate. Let's say I have this triangle. Let's pretend this is, that's 90 degrees, and pretend this one is 35 degrees. If I have another right triangle that also has a 35-degree angle, well, then they have to be similar, right? And that's just because of AA, because we have two congruent angles. Well, the fact that they're right angles also makes the side lengths very unique and have a relationship because of the Pythagorean theorem. The way that every right triangle sides work together has to work in a certain relationship to make the Pythagorean theorem work. So right triangles are really special anyway. Okay, so because this is true, we can look at the ratio of each pair of sides within these triangles, and those ratios are going to be the same. So what we're saying here is that if I took the ratio of, say, this side to this side in a right triangle with a 35-degree angle and compared that to the ratio of this side to this side, those ratios are going to be the exact same. And that would be true for any right triangle with a 35-degree angle. Likewise, if I just did another pair of sides. So let's say I looked at the ratio of this side to the hypotenuse, or in the other triangle, this side to the hypotenuse, that ratio is going to be the same in those two triangles, and it will be the same for every right triangle with 35 degrees. And again, this angle measure is not a magic number. The 35 degrees is not magic. That angle could be anything. I could be talking about a right triangle with a 42.5-degree angle. I could be talking about a right triangle with a 17-degree angle. Every right triangle with a 17-degree angle would have these same ratios. When they figured this out, that was true, these things got created called trigonometric tables that showed these ratios. And you could use the tables to figure out what the ratios were for any specific angle in a triangle. As we progressed in time and we had technology, those tables got put into computers and calculators. And so your calculator will give you what those ratios are for any particular angle. I know it's still a little bit confusing, but that's like the basic background. We are going to walk through what all of this means today and figure out what these ratios actually are. Okay, before we can do any of that, we need to understand how we're going to refer to different parts of a triangle. I have two the same triangles here, and notice that this one on the left is saying, if I'm talking about this angle, just like this angle right here, then there's going to be certain words that we're going to use to refer to the other sides, to all the sides on the triangle based on that angle. So notice the numbers here. We're going to go around and follow the numbers, 1, 2, 3, 4. So if I'm talking about that angle, then I would call this leg right here, I would call that the adjacent leg. It is the leg right next to that right angle. Okay, let's keep going around our circle. Then I would call this leg down here, so this leg, I would call that one the opposite leg, or really just the opposite side. And then this one is the easy one because we always know what this one's called, and that's just called the hypotenuse. Okay, now in the second picture, notice now I've changed it so that I'm talking about this angle down here. So now I'm dealing with this angle. Okay, so let's go around our circle and follow the numbers. This time, I would call this leg here the adjacent leg or adjacent side. It's right next to that angle that I'm talking about. Continuing around my circle, I'm going to call this leg the opposite one. And then finally, we're going to call this one, as always, the hypotenuse. That one doesn't change. So basically, the words adjacent and opposite are going to refer to the two legs, whether they're right next to the angle that we're talking about or opposite across from the angle that we're talking about. So adjacent and opposite are going to become super useful words that we have to understand. We're going to practice that. Okay, so in this set of questions, all we're going to do is label the sides adjacent, opposite, and hypotenuse in relation to a given angle. So in number one, we're talking about angle A. So we're looking at this angle right here. So we're just going to label all three sides. Let's start with the easy one. Hypotenuse. I'm going to abbreviate here because I can't fit all that. It's hard to write with this pen. And for the other two, the side right next to that angle, that one is the adjacent one. And then the one that's across from it, that one is the opposite one. Okay, why don't you go ahead and try the next three by yourself? Just give it a quick pause, try the next three, and then come back and see how you did. Okay, how'd you do? I hope you got those labeled correctly. If you didn't, go ahead and take a minute and fix them now. Hopefully those words make sense. We've got adjacent, opposite, and hypotenuse. Okay, next, if you can find the other paper in your packet that has the three triangles on there, all in one paper. And normally in class, we would take the time and measure all of the sides of those three triangles, for the big triangle, the medium, and the small triangle. And then we would record the measurements that we found for the opposite, hypotenuse, and the adjacent sides, and we would create these ratios. Now on here, I don't know how to do that measuring, so I'm going to just measure it for you and give you those labels. We're going to go ahead and write down the numbers, and then we're going to come back to this screen and fill in this chart. So just wanted to let you know what we're going to be doing. So go ahead and find the paper with the triangles. Okay, so here are the triangles. So if you haven't already grabbed that paper, I've turned it just to fit it on my screen here better. So if you want to turn it as well, I'm going to go ahead and label the sides. I've measured all these with a centimeter ruler just so I could use decimal answers rather than fractions, just to make our work a little bit easier. And let's go ahead and just fill these in. So for the big triangle, the hypotenuse is 25 centimeters. And the short leg is 14.4 centimeters. And the long leg is 20.6 centimeters. And for the little tiny one, the short leg is 5 centimeters. The hypotenuse is 8.8 centimeters. The long leg is 7.2. Let me turn that the other way. centimeters. Okay, and then for the medium one, the hypotenuse is 17.2 centimeters. The long leg is 14 centimeters, and the short leg is 9.8 centimeters. Okay, so notice in each triangle that there's one angle that I've marked And just to highlight it here for you, so this is the angle that we're referring to in all three of these triangles. And I also should have mentioned earlier that these three triangles are all similar. They are all right triangles that have a 35-degree angle. And so the angle that's marked is that 35-degree angle. So when we go to the chart in just a second, we're going to fill in some ratios. We're going to be referring to this angle that's marked, the one that has that little mark on it. Okay? Okay, so we're going to take the numbers from those triangles and we are going to write these particular ratios, which I'll talk much more about why I chose these ratios in a bit. But we're going to write down these ratios for each triangle. So I'm looking at the big triangle first, and I'm going to make the ratio of the opposite over the hypotenuse. And this is all in relation to that angle that was marked. So from that marked angle in the big triangle, the opposite is 14.4. And then the hypotenuse is 25. We're going to get our calculators out in a bit and make these all, like divide them out and get a decimal. But let's go ahead and just fill in all the ratios first. Okay, so then for the big triangle again, from that same angle that's marked, we're going to do the adjacent over hypotenuse. So the adjacent is the leg next to that angle, which is 20.6. And then over the hypotenuse, which is 25. And then the opposite of that, from that same angle again, the opposite was 14.4. And that will go over the adjacent side, which was 20.6. Okay, and next for the medium triangle, we're going to do the same exact ratios. So looking from that marked angle, the opposite from that one is 9.8, and the hypotenuse is 17.2. And from that same marked angle, the adjacent side is 14, and the hypotenuse is 17.2. And then the opposite was 9.8, and the adjacent is 14. Okay, finally, we're going to do the small triangle. So the little teeny tiny one, and from that marked angle, the opposite side is 5, and the hypotenuse is 8.8. And the adjacent side from that marked angle is 7.2, and the hypotenuse is 8.8. And the opposite side was 5, and the adjacent one was 7.2. Okay. So now that we have these ratios done, we're just going to get our calculators out and we're going to divide these numbers, each of the ratios, to change it from a fraction to a decimal. And then we're going to make some observations. Okay, so I've gone ahead and calculated these out for you and we'll write them down together. So for the big triangle, the first ratio of the opposite over hypotenuse. Oh, and we're going to round all of these to 4 decimal places, which might seem like more than we've ever really done before. And you'll see why in a little bit. So this first one is going to be 0.5760. And then the adjacent over hypotenuse is 0.8240. And the opposite over adjacent is 0.6990. Okay, for the medium triangle, the opposite over hypotenuse is 0.5698. And the adjacent over hypotenuse is 0.8140. And the opposite over adjacent is 0.7000. And finally, for the small triangle, the first ratio is 0.5682. The adjacent over hypotenuse is 8182, 0.8182, and the opposite over adjacent is 0.6944. All right, so what do these numbers mean? So remember way back in the beginning of this lesson, the very first thing we talked about was how if you had any right triangle with a 35-degree angle, which is what we are working with here, that obviously they're all similar, and because of AA, and the ratio of different pairs of sides of one triangle would be the same for all of those triangles. So basically, I want you to take your mind's eye and look at each of the columns here. So I want you to pay attention to this column because all of these are the ratio of the opposite over hypotenuse. And if you notice, these three numbers are really, really close. The reason they're not exactly the same is because, well, one, I've taken them out to 4 decimals, and 2, I was measuring with a ruler, and I did it to the nearest tenth of a centimeter, so to the nearest millimeter, and they're not perfect. But if I had rounded these to the nearest tenth or even hundredth, they would be really, 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 really close. So, gosh, yeah, if I did the nearest hundredth, I would get 0.58 for this first one. I'd get 0.57 and 0.57. Still a little tiny bit off, so definitely human error in my measuring, but you can see they are very, very similar. Okay, and then the second column, so I want you to look at that column here. Look at these three ratios, and notice that, again, they're very, very close. Definitely to the nearest tenth, they would be the same number, and nearest hundredth, they're close. We've got 0.82 for this one, 0.81 and 0.82 if we did to the nearest hundredth. So again, human error in the measuring is what's making this be off a tiny bit, but basically what it's saying is the adjacent over the hypotenuse of any right triangle with a 35-degree angle would be close to these numbers. And then look at the final column. So we've got the opposite over adjacent, looking at these three numbers. Again, very, very close. If I rounded to the nearest hundredth, I would get 0.70 for the first one. I would get 0.70 for this one and 0.69 if I rounded to the nearest hundredth on that one. But very close. Okay, so again, what does all of this mean and how is it helpful? So we have names for these ratios is the first thing. This first column, whenever you see opposite over hypotenuse, this stands for the sine ratio. The word sine is actually spelled S-I-N-E, and on the shortcut button that you're going to see on calculators and on computers, it just looks like S-I-N. It looks like sin, but it's actually said sine. It's just an abbreviated version of that word. It's S-I-N-E is the sine ratio. Anytime you're dealing with the adjacent over hypotenuse, this is called the cosine ratio. And then the shortcut that you're going to see on calculators and computers is just COS for cosine. And then finally, the last one, the opposite over adjacent. This is called the tangent ratio. And the shortcut you'll see is just TAN for tangent. Okay, so how are you going to remember this? Well, there's a nice little mnemonic that will help you. And you may have heard of this mnemonic before, but you may not have. And the mnemonic is the word SOHCAHTOA. This is what it looks like. S-O-H so cut is C-A-H and then TOA. What does that mean? So the first letter of each of those parts. So we've got the S stands for sine, and then it's the letters stand for opposite and hypotenuse. And it goes in that order. It's opposite over the hypotenuse. So is sine, which is opposite over hypotenuse, which is what you're seeing in this column. C stands for cosine. And then this tells you it's adjacent over hypotenuse. And it's in that order. Adjacent's on top, hypotenuse is in the bottom. So that's helping you to understand this column. And then the final one is tangent. So T for tangent. And then it's telling you it's going to be opposite over adjacent. And again, it's going to be in that order. So I know it's still not super clear about how we're going to use these ratios, these sine, cosine, and tangent ratios. But just to kind of give you the big picture, big overview here, basically if you have a right triangle and you know one of the other angle measures besides the right angle, you will be able to use these ratios to help you find what some of the side lengths are of that triangle. Or vice versa, if you know it's a right triangle and you know the side lengths, these ratios will help you to find what the other angle measures are. All because every right triangle with a specific angle measure is going to have a predictable sine ratio, cosine ratio, or tangent ratio. We know what those decimals are going to be, and those decimal numbers, those ratios, are all programmed now into calculators and into computers. I don't know if I mentioned this earlier or not, but there is, before computers and calculators, there used to be this thing called a trig table. I encourage you to Google that and look up a trig table, and it's just a big list of decimals like we see here. It's got these decimal values for the sine ratio, the cosine ratio, and the tangent ratio for every whole number angle measure that could be in a triangle. So basically, in a triangle, if you have a right angle, your every other angle has to be acute. It has to be anywhere from 1 degree up to 89 degrees. And so there's a predictable sine ratio for a 17-degree angle. There's a predictable cosine ratio for a 17-degree angle, and there's a predictable tangent ratio. So this table, that if you look it up and see what it looks like, shows you all those decimal values for every given angle of a triangle. We don't have to use those tables anymore, though, because like I said, your calculators and your computers all have those numbers stored inside of them. Okay, so this image is just an overview of the different ratios that we just talked through. If you haven't written down that mnemonic of SOHCAHTOA, find a place and let's write it down now. So we have SOHCAHTOA. And I firmly believe that you are never going to forget this mnemonic again. It's going to be stuck in your head. You're going to use it so much. I can honestly tell you, I don't do a trig question without this mnemonic. And I've been doing trig questions for a long time in my math career. So again, this S stands for sine. It tells you it's going to be opposite over hypotenuse. That's what this is showing you here. It's the length of the opposite from angle A over the hypotenuse. And then we have C stands for cosine, and it's the adjacent over the hypotenuse. That's what this one's showing you here. It's the adjacent one to angle A over the hypotenuse. And then finally we have TOA is T for tangent, and that's the opposite over the adjacent. SOHCAHTOA, it's going to be your best friend. Okay, so we're not going to find any missing angles or sides just yet. We're going to just practice writing our trig ratios, like understanding which numbers need to go in which spot. Again, I want you to write it out. Let's write out SOHCAHTOA one more time here, so you can have it right in front of you. And let's just go through and practice these ratios. So the first one says we want to find the tangent for angle A. So we're looking at angle A, and we want to do the tangent. It's telling me I want to do the opposite over the adjacent. So from angle A, I look at the opposite, that's 3, over the adjacent, which is the one right next to it, but not the hypotenuse. So that's 3/4. We could make them decimals, but I'm not worried about your skill level in doing that. Let's just leave it as a fraction. For most things you're going to do with these ratios, we will make them decimals, but that's not my concern right now. I just want to make sure you understand where to get the numbers from for each ratio. Okay, so now we're going to do the tangent for B. So we want to do from B the opposite, which this time is 4, over the adjacent, which is now 3. Okay, next we're going to move on and do some sine ratios. So now we're looking at doing the opposite and hypotenuse for the sine. So we're doing sine of A, so we're back to A again, and we want to do the opposite, which is 3, and put it over the hypotenuse, which is 5. Sine of B, again, the opposite from B is 4, but the hypotenuse is still 5. Okay, and we're going to move on to cosine ratios. So cosine tells us we want to do adjacent and then hypotenuse. Okay, so the cosine of A, so we're looking at here is our base angle. The cosine tells me to do the adjacent, which is the one right next to it, so that's 4, over the hypotenuse, which is 5. And then the cosine of B, so the adjacent from B is 3, over the hypotenuse, which is 5. Okay, so next we're going to talk through how we can use technology to find the actual ratios, sine, cosine, or tangent of different angles. You are able to do this with a graphing calculator or with Desmos. Some of you do have your own graphing calculators, and that's fine. I will mention briefly what you do with that calculator, but I'm mostly going to do my explanations through Desmos, since that's what you're going to be using in your math classes and on future SOL tests. One quick note I need to make is that angles, you are used to always measuring them in degrees, which is what we are going to be continuing to do here. But there's actually another way to measure angles, which you haven't learned about yet, which you will learn about in Algebra 2, and that's called radians. So every calculator, or whether it's on the computer or on a graphing calculator, can do these ratios with angles that are measured in degrees or in radians. And later down the road, you will use radians much more often than you will use degrees. And so by default, most technology is set up to do sine, cosine, and tangent ratios with radians. So you need to change that. You need to change it to degrees to make that happen. If you are on a graphing calculator, all you have to do is press the mode key. And if you press that, you're going to see RAD for radians and DEG for degrees. You're going to want to change that by sliding your cursor over to degrees before you do anything with trig ratios. If you are on Desmos, you're going to click on the wrench in the upper right-hand corner. So if you're on a Desmos calculator screen, if you want to take a moment and pause and go and open one up on your computer, and once you click on the wrench, you're going to choose degrees at the bottom of the little pop-up window that comes up. This is a really important step. Imagine if you didn't do this, every single answer would be wrong. And if you were taking like a multiple choice test or an SOL test, you would be wondering, why are your answers not in the answer choice list? And it would be because of this. So I will remind you about this a lot from here on out. But just try to remember, if you are taking a quiz and you see 4 choices and your answers are not there, it's probably because you have your technology set up to do the angles in radians instead of degrees. So just keep that in the back of your mind. Okay, so at this point, I'm going to be doing this all with Desmos, and hopefully you are too. So if you either maybe have another window open that you can see your Desmos screen at the same time as you're listening to this, or you can go back and forth. Go ahead and make sure it's in degrees at this time. If you have a calculator at your house, that's fine, and you want to do that, just make sure it's in degrees. Okay, so all you have to do in Desmos is on the left side where you have like the place you type stuff in. Just type in, you can type in the word sign, like SIN, you can just type it yourself. Or if you want to use the keyboard at the bottom of the Desmos screen, on the right hand side, you will see a button that says functions. If you click on that, a whole bunch of trig functions pop up, more than we're ever going to learn this year. Some of these you'll learn in Algebra 2 and some even after that. But you'll notice the first three in the first column says sine, cosine, tangent. So you can click on that inside the functions button. You can click on sign, or you can just type it in. I think it's just easier to type those three letters in, SIN, and then the number 42. So you type that in, you hit enter, and you'll get a decimal. And what you should see on your screen is the decimal, and we're going to always use 4 places, is 0.6691. If you're not getting that, if you've got a negative number, it's because you still have it in radians. That's a huge clue. Sine, cosine, tangent ratios should never be negative. If you're getting a negative number, it's because you have it in radians. It's not the only like you'll see other numbers too. So that's not the only thing that's going to happen if you have it in radians. You won't always get a negative, but that's just a big clue for you. Okay, let's try the next one. So you're going to type in on Desmos cosine, just type in COS, and then 68. And you should get the decimal 0.3746. And then the tangent of 25. So just type in TAN 25, and you're going to get the decimal 0.4663. So to try to remind you again what these numbers actually mean, what this is saying is if I have a right triangle where one of the angles is 42 degrees, I'm just going to draw a quick picture here. This is not accurate. This is just a sketch. If this angle here is 42 degrees, in any triangle that looks like that, that's a right triangle with a 42-degree angle, the ratio of the opposite side from that, so this opposite one, so this side right here, the ratio of that side over the hypotenuse for every right triangle with a 42-degree angle will be 0.6691 every single time. And then just to remind you what the second one is saying, if I just sketch another triangle here, let's say I have a triangle that looks like this, and let's say that this angle is 68 degrees, then the cosine, which is the adjacent, so it's saying the ratio of this side over this side for any triangle that's a right triangle with a 68-degree angle, that ratio for any triangle like that would be 0.3746. And then the same thing for that tangent. If you have a right triangle with a 25-degree angle, then every single triangle like that would have the opposite over the adjacent would be 0.4663. Every single triangle like that. In the next couple videos that you're going to be doing, you're going to take these ratios and you're going to learn how you can use them to find a missing side or to find a missing angle. You're also going to be looking at how to use sine, cosine, and tangent ratios to find things called the angle of elevation or the angle of depression. And finally, you're also going to learn about a way to find the area of a triangle using a sine ratio, which might seem a little weird, but you can do that. So lots of good things coming up. For now, all you have to remember for this video is SOHCAHTOA, sine, cosine, and tangent.